I can go ahead and jump into this now, and we're going to jump over to just a bit of an introduction into like what are world models. And so for me, the first paper that kicked this off was neural radiance fields. And so representing scenes as neural radiance fields for view synthesis is the name. The lead author was Ben Mindenhall, and it was done at UC Berkeley. And this is a really awesome paper where for the first time they kind of say, what if we bake the inductive bias of cameras into AI models? And so you say if we shoot a bunch of AI rays into the world, and then we have the model respond to each ray with a color, that machine learning model ends up representing the scene. And when we bake it with the camera, we can then move around that camera. We can train it to respond to different angles. And then afterwards, we can take that camera and we can move it around and render novel angles we might have seen before. So we can just look at what some of these samples look like. And so here's an example of them being able to move the camera around and kind of see this big, awesome looking dinosaur from many different fun angles. Here's some kind of pictures of that thing that I was talking about. So if you look at this, you can see here's these camera rays I'm talking about. And so each kind of image here would be a different camera angle. So they train this by taking a picture of this dinosaur from many different angles. And then you simulate a camera, you cast a bunch of rays into the scene. This block here is the model. So the model is a big function, and that function accepts X, Y, Z, and directions in space. And so that's the ray that you have going through this function. And then that function, given a ray being shot through it, has to return any color. And so if you take one of these rays at every single point for this entire image, and so if we say 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, 1, 3, blah, 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 until we get this full grid of pixels, and we sample all of those from our model, what we get is a model that can represent a scene from any given camera angle. And so you can see these sorts of things. They train it on 3D objects, and then we can spin these 3D objects around. So you have an AI model that is a 3D object. So instead of needing to model an actual 3D object, you can go out, take photographs of things, and then turn it into something. Here's a cool angle where they show the depth underneath. So without color, what is the 3D kind of volumetric representation of this? Here's them inserting a random ball into the scene. So they say, and now that we have a 3D model, we can sort of put these little balls into the scene and render that around. Here's one of the meshes of this 3D object they have. And some more kind of information of their follow-up works. And so this was actually about 6 years ago now, so it's been quite a while. Feels like just yesterday that the field kicked off, but since then we've seen kind of rapid progress on these 3D representations. And so the most recent trend of this work is 3D Gaussian splatting. This was 2023, and this kicked off a newer kind of version of this work where instead of having an actual model in the middle, you have 3D objects. So we go back to actually having real 3D objects, and so what they do is they make, what if we take a billion little Gaussians and we scatter them around this scene, and we say, can we optimize these and fit them to be in the right spot? So that if we do the same thing where we train from every camera angle, and then we render each camera angle, we can move around these little balls until all of the balls are in the right spot so that it represents this smooth kind of representation in the scene. And so you'll see these similar kind of videos where we can capture something, and then afterwards we can move our camera around as if we could move our camera anywhere, even if we didn't take video from all of the original angles. So as long as we cover some reasonable amount of space, we can kind of do this afterwards. And they show this compared to different NeRFs and things like this, and one of the big things they show is speed. And so the rendering of this goes up to 130 frames per second. And so one of the reasons this really took over is because to do a NeRF, you have to take this giant neural network and you have to run it every single time a ray goes through. And every single time you have a frame, you have to do a bunch of these rays. And it just ends up being very, very expensive. And so this FPS is for rendering. And so if we have a bunch of blobs and 3D objects, turns out those are really, really cheap to render because your graphics card can just do that. It knows how to render a bunch of 3D balls. Rendering a 3D ball is like the fastest thing that a graphics card can do. And so you can see it has better results, it's more clear, trains faster, kind of a big exciting breakthrough in the field. And they're just also easier to work with because you actually have these 3D objects instead of being stuck with this kind of awkward neural network that you don't know what to do with. And then recently, people have taken these things farther, and this is where we start to get to stuff that looks more like world models. So now we're back to 2 years from now. They've started to train these on video. So this is the same approach. We've got a bunch of 3D balls in a scene, but we can use a time variable, and we can slide this time variable back and forth. And then we can see things that are really cool and animated, like this great video of this guy lighting this spray on fire, which is just awesome. My favorite demo of all these. And you can see the cameras moving around, and it's able to render this fire kind of moving. If you notice, the resolution isn't perfect of the fire. Not as easy to get those things accurate, so that's some of the trouble that's left in the field. Here's another version of this with a bit of a breakthrough of what's underneath, what do our points look like, a bit of a longer camera swing, we can kind of see what's going on. And you could imagine stuff like this would be really cool for Hollywood. There's maybe tons of different applications of this. It works on many different scenes. And so what's now coming out is, instead of just memorizing one single scene, can we start to go to something that looks like a world model? And so there was a paper recently called TokenGS. This comes out of NVIDIA, and what they do is they pre-train a model. So just like LLMs are trained on tons and tons of text, we can pre-train our world model on tons and tons of video and tons of images. And then instead of having to optimize a bunch of these splats for every video in a specific way, we can just have a model that takes a video and then outputs a scene. And so this is one of the cooler papers recently on this. You may have also seen people making Genie, which does these video games you can play. So you feed in an image, and it generates a world you can run around and play in as a video game. So this would just be given some set of images, you generate these splats. And so you can see, it has some flaws where if we haven't seen here before, it's not going to generate those splats. If we go behind the bookshelf, it's kind of broken. And so we still are in a research phase. These things aren't perfect. They're not going to do your LLMs and beat Erdos problems, but this emerging field of research is getting rapidly better and better, where this is in a feed-forward network, and so we can look what that means. Images go in, feeds it out, and makes our Gaussians just sort of instantly. So none of this long kind of tail optimization from these old papers. And so that's what is a world model. And so in the last week or so, I decided I'm going to train my own. This paper was really cool and works on surprisingly minimal amounts of data. And I think there's a ton of stuff that I can do for that. And so I started up this project called, currently named Dina World. Will probably be getting renamed to World Models at Home soon. And just a bunch of my loose notes here, not a super well-structured README. But I have a couple of core beliefs of how I think I can push forward world models. And one thing is, this paper just trains everything from scratch. So it's a whole brand new model, doesn't learn from any other models out there. I think there's a very cool trend around papers like Marigold, prediction. So this was a model where they took Stable Diffusion and they said, if we do Stable Diffusion, we can train Stable Diffusion to not just generate images, but to generate depth, give it an image. And so they kind of say these base models that know how to generate images also understand the 3D world. And so you've seen the same thing kind of happen, and I think you can do something similar with taking a base 3D video model and training that to emit 3D worlds just like this one. So you can imagine, say we take this same approach here, and instead of feeding in to our base normal model, we could take a video diffusion model, strap it on the front here, replace this with a pre-trained model that understands videos really well, and then have it emit a 3D world. So instead of having to train our entire 3D model from scratch, we're basing it off of one of these models that understands 3D and video already quite well. That's one of the things I was thinking about. And so I kind of think of this as 3D is a modality, not necessarily a new model, and video is the world. So if you think of a video model as training for the world, and diffusion models are already learning a world model, can we extract that to make a sort of interactive 3D modality of that instead of just a fixed video camera on that? So I've outlined kind of some of where I'm at here and what I've done. And mainly what I've done is reproduce this TokenGS paper as a baseline and kind of some other small baselines around that, including adding one of these video encoders. And so we're going to start jumping into the code here.